Good evening. Today we'll start with a new chapter that is of the MCH-004. The first unit of this of today's class is Introduction to Electroanalytical Methods. So today we will discuss the basics concepts of electroanalytical method. So first we will also study about electrochemistry, different electroanalytical methods and the classification, the relationship, and finally we will study the summary of the different electroanalytical methods. So before going to the different electroanalytical methods, we should start with certain basic concepts. So the basic concepts regarding here electroanalytical chemistry is first the electrical units. The electrical units we will begin with ampere. So we know ampere is the unit of current. So it has been named after the French scientist, that is AM ampere, and it is represented as capital A. So 1 ampere of current is equal to the unvarying direct current when it is passed through a silver nitrate solution under particular conditions. So here 1 ampere of current, it will deposit silver at the rate of 0.00118 grams per second. So when this much amount of silver is deposited, then we say 1 ampere current has been passed. Then there is a second unit that is called as ohm. Now the ohm is the unit of electrical resistance, and it is called as ohm in honor of the German physicist, that is G.S. Ohm. So the resistance that is offered by a uniform column of mercury with direct current is equal to, we call it as 1 ohm. So this is the unit of electrical resistance. Then there is another term that we call it as volt, which is represented as capital V. So the unit of electromotive forces and the potential difference, that are called as volt, and this volt capital V has been taken in honor of an Italian physicist, C.S. Volta. So the unit volt, it is derived from the units of current and resistance via the Ohm's law. And we know what is Ohm. Force which when applied to a conductor whose resistance is 1 ohm, and it will produce a current of 1 ampere. So here that is how we define a volt. Then there is another unit that we call it as coulomb. So coulomb is the usual unit that has been mostly considered to express the quantity of electricity. So here the coulomb, this coulomb, it represented as capital C, and it has been derived in honor of the French physicist C.A. Coulomb. So 1 coulomb is defined as the constant current which corresponds to 1 ampere flowing for 1 second of time. So that is how we define a coulomb and represented as capital C. Then coming to Faraday. So the quantity of electricity that is associated with one equivalent of chemical change in an electrochemical process is called as Faraday. So Faraday is represented as capital F. So 1 Faraday is equal to 96494 coulombs. So here Faraday has been named in honor of the English scientist M. Faraday. Then there is another unit which is called as Siemens, that is represented as capital S. So Siemens is the unit of electrical conductance, and here it is given as S is equal to A by V, where A is equal to the ampere and V is the volt. So this is how we represent the different electrical units, that is ampere, ohm, volt, coulomb, Faraday, and Siemens. These are the certain basic units in electrochemistry. Then now coming to some basics laws of electrochemistry. So first is the Ohm's law, which we all know that it is the mathematical relationship between three fundamental electrical quantities, that is the electromotive force E in volts, the current I which is measured in amperes, and the resistance R which is measured in ohms. So according to this Ohm's law, This states that the current flowing in a conductor is equal to the potential difference between any 2 points divided by the resistance between them. That is, mathematically we write I is equal to E by R or E is equal to IR. Sometimes this volt, it has been written in V, so we can also write it as V is equal to IR. So this is how we represent Ohm's law by V is equal to IR. Then coming to Faraday's law. So Faraday's law, here it states the quantity of current in coulombs that is associated with an electron transfer process. It is directly proportional to the number of equivalents of the substance that is involved in the chemical change which is occurring at the electrode. So the number of equivalents of the substance that is present, that is number of equivalents of the substance that is undergoing the change, can be obtained from the number of moles divided by the number of electrons that take part in the reaction. So this Faraday's law, it can be written as Q is directly proportional to number of equivalents, where Q represents the quantity of current in coulombs, or we can write it as Q is equal to F into the number of equivalents, or finally we can write it as Q is equal to F into the number of moles per N. So here F is the Faraday constant, and which we know it is equal to 96494 coulombs. N is the number of the electrons that take part in the chemical reaction. Like for here in the reaction given below, O plus N number of electrons which forms the reduction product R. So the number of electrons that takes part in this reaction is given N. So using this number of moles, the N value from this type of reaction, we can calculate the quantity of current Q from the Faraday's law. Then coming to electrode potential. So the understanding of electrode potentials is very basic to electroanalytical chemistry. So first we need to understand how an electrode potential is developed. So whenever two dissimilar conducting phases, they are brought in contact, an electrical potential, it develops across the interface. So first, let us, to understand this, let us consider a metal solution interface. So we will consider a metal M that is placed in a solution containing its ion Mn plus. So here the metal, it is composed of the metal ions and the electrons. Both the phases, the metal and the solution, they contain metal ions Mn plus, but the activity of the metal ions in the metal will be different in the solution and inside the metal. So that is why we see two different types of the activities of the metal ions. So let us, so for two types, we will consider two types of metals here. One is copper and one is zinc. So here we will put them in their salt solution. Like here in figure 1.1, you can see two different metals have been taken, copper and zinc. And in the first case, that is the copper case, it is a less active metal, and when it is placed in a solution of copper sulfate, some of the copper ions, they may deposit on the copper metal, accepting electrons from the conduction band and leaving the metal with a small positive charge, and the solution, it develops a small negative charge here at the copper sulfate interface. Now in the second case, that is in the figure 1.1, in the second case, we have taken zinc metal. So now we know here zinc is a more active metal. So here the metal gets a small negative charge and the solution, it acquires a small positive charge. So here the reverse case occurs. So however, in both the two cases, the positive and negative charges, they will be located at the surface of the metal solution, and thus that is called as the interface. So because here we see the electrical double layer is formed, that is because of the difference in the potential between the metal and its solution. This potential is called as the electrode potential. So this is how we define an electrode potential, that is the difference arising between the potential of the metal and its corresponding salt solution. Then coming to measurement of electrode potentials. However, we know there is no direct way of measuring the potential difference between an electrode and a solution, but this can be measured when by taking a reference electrode or a standard electrode. So such reference electrode, it was first proposed by Nernst, and we call it as a standard hydrogen electrode. So that is given as SHE, and it was given, the value was given as zero potential at all temperatures. The potential for standard hydrogen electrode SHE is zero irrespective of any temperature. So by universal agreement, the standard hydrogen electrode has been chosen as the reference electrode by all the chemists across the globe. So thus the electrode whose potential is to be measured, it is first coupled with a standard hydrogen electrode, and then the EMF or the electrode potential of the resulting cell is studied. So this is how we calculate the electrode potential by comparing its potential with that of SHE, that is the standard hydrogen electrode. Then there is a very important term in electrochemistry, that is liquid junction potentials. So what are liquid junction potentials, or it is commonly they are called as LJP. So when two different electrolyte solutions, they are brought into contact, then an electrical potential difference, it arises at the zone of their contact or at the point of their contact. So this potential difference is called as liquid junction potential, or it is represented as EJ, or sometimes it is called as diffusion potential. Now this is caused due to the diffusion of the ions from the region of higher concentration to the region of the lower concentration, and it depends on the mobility of the ions that are present in the solution. So various types of liquid junction potentials are possible. Like one simple type of LJP is illustrated here in figure 1.2. Like suppose we prepare a quiet interface between two solutions containing the same electrolyte but at different concentrations, such as zero point 0.1 molar HCl and zero point 0.01 molar HCl. So when these two concentrations, they are right, and this is called as concentration gradient. However, but what we see now, we will look into the mobility of H plus ions and Cl plus ions. The H plus ions, they are smaller and they move much more rapidly than the chloride ions, and it has been indicated by this arrow. So the H plus ions, they outrun the Cl minus, and this there is a slight tendency for the charge separation at the right side of the junction. So what happens here is, because of the mobility of the faster mobility of the H plus ion from the left to right side, so there is a charge it develops. So what happens is, as a result, the right side, it acquires a slight positive charge, whereas the left side of the cell, it acquires a slight negative charge. So this is how a LGP functions. So the liquid junction potential, it may vary the over a considerable range depending on the conditions of the cell. So these potentials, they can be minimized using a salt bridge containing a concentrated electrolyte solution of a cation. Like for example, potassium and chloride ions, they have comparative mobilities. So thus salt bridge of saturated aqueous potassium chloride, they have been widely used to minimize the effect of this liquid junction potentials. So LJP, since they change the potential in the cell to minimize their effect, in all the cases or in most of the cases, saturated aqueous KCl solutions, they have been used. Now coming to electrochemical cells. So an electrochemical cell, it consists of two metallic electrodes that are immersed in either the same electrolyte solution or in two different solutions that must be in electrolytic contact. So an electrochemical cell, the basic function is to convert the chemical energy into electric energy, or vice versa, depending on the type of the cell reaction, like whether it is spontaneous or it occurs spontaneously when the electrodes are connected and it converts chemical energy into electrical energy. It is called as the galvanic cell or the voltaic cell. Alternatively, the basic function of a galvanic cell is to convert the chemical energy into electrical energy. Sometimes this galvanic cell is also called as voltaic cell. So then the cell where the cell reaction occurs non-spontaneously, it is called as electrolytic cell. So here what happens is, so some we will further discuss the concept of this galvanic cell and electrolytic cell. So first we will start with galvanic cells. So here in a galvanic cell, here in figure 1.3, a galvanic cell has been shown. So the system, it comprises of two electrodes. Those are called as hub cells. So here the two electrodes, they occurs where the energy associated with the chemical reaction, it is converted into electrical energy. So a galvanic cell or a Daniel cell, it converts the chemical energy into electrical energy. So this is how a Daniel cell it is worked. So when we look into the two half cells of these reactions, we can see in one half cell of the left hand side, zinc sulfate is present, and the other half cell, it contains copper sulfate solution. So with these two half cells, they are connected through a salt bridge, and the salt bridge that mostly uses aqueous saturated potassium chloride solution. So here the salt bridge, it is present in the U shape. So the zinc strip here that is present on the left hand side, it is immersed in zinc sulfate solution. It constitutes the one half of the cell, and the copper strip which is present on the right side of the electrode of the cell, it constitutes the other part of the cell. So we call it as galvanic cell because this was invented by the scientist Luigi Galvani. So this cells has been developed mostly to supply electrical energy before generators were made available. So that is the first utility of galvanic cell. Now when the circuit is closed, the cell operates spontaneously. So how does this cell operate spontaneously? The copper has a higher positive potential than zinc. So as a result, the electrons, they flow from zinc to copper in the outer circuit through the wire. The flow of electrons is called as an electric current. So as the electrons start flowing from one side to the other, then electric current is generated in the cell. So conventionally, here the flow of current is considered opposite to the direction of the flow of electrons. So this is the general convention. The cell reactions are the oxidation and the reduction products. So what happens here is at the copper electrode, the copper ions are reduced when electrons are consumed, and thus this part, that is the copper electrode, that is called as the cathode. However, at the zinc electrode, the oxidation occurs, and that is why it is called as the anode. So this is how we have differentiated the copper, the cathode part, and the anode part of our Daniel cell. So now coming to writing of the cell reaction that occurs in this Daniel cell. So here to write the electrochemical reaction, so overall we have to first write the half cell reaction followed by the integration of the two half cell reactions. So here we first, it is reasonable to write the cell reactions like in a logical manner following a convention. So the convention is that the anode, that is the negative electrode, is always on the left and the cathode is always on the right. So here the logic is that the anode reaction should be written here on the left side and the cathode reaction should be written here on the right side. So here this indicates that the chemical reaction in the cell, it follows the way that occurs in it, how the chemical reaction is occurring inside the galvanic cell can be known from the way we write the electrochemical reaction. So here, for the above galvanic cell, we can write the equation as here it is shown in this equation. So here we can see there is a vertical bar between zinc and Zn2 plus. So here it indicates the metal solution interface here, and here also for copper 2 plus and copper we see a single vertical bar. So it also indicates the metal and the metal solution interface. However, when we look into these two, we see a double bar that is shown here. So here the double bar here it represents the liquid junction potential, and that separates the two cells. So this is how we generally we represent the normal we write the electrode cell reaction. So here then this is the overall reaction that has been shown. Now what we will do is we will convert the we will first break down the overall reaction into the two half cell reactions. So for this purpose what we will do is the here in equation 1.4, here in equation 1.4 we can see that in this reaction, here it is shown as zinc, it forms Zn2 plus 2 electrons here in equation 1.4. So after this, when we look into the other half cell reaction, it is given as copper 2 plus aqueous forming, taking up 2 electrons, it forms copper from equation 1.5. So the net cell reaction can be obtained by adding the equations 1.4 and 1.5, and finally we get the net cell reaction as zinc plus Cu2 plus forming Zn2 plus copper. So this is the overall cell reaction for the above cell. Then the EMF of the galvanic cell, this is the overall cell reaction. Then now we have to calculate the EMF of the galvanic cell. So here it is the difference between the potential of the two electrodes and the potential difference at the zone of the two electrolyte solutions. So now what we will do, we will find out the potential difference between the two electrodes. So here it can be written as the overall cell potential can be written as E cell minus is equal to the EMF of the right part and EMF of the left part. So here that is, or in simplified terms we can say that the cell potential is that of the potential of the cathode minus potential of the anode, that is given in equation 1.8. So here that is E potential is the potential of the right electrode and E left is the potential of the left electrode. So now here using this equation 8 we can write the EMF of the cell for the Daniell cell total can be written as E cell is equal to the potential for the cathode reaction, that is Cu2 plus copper minus the potential of the Zn2 plus 2 Zn. So the cell EMF it is always positive, so therefore it is written in such a way that the E cell becomes positive. So this is how we can calculate the potential of a overall cell. Then now coming to a very important part of electrochemistry, that is Nernst equation. So Nernst equation has found profound applications in electrochemistry, and this was it is a quantitative relation between the equilibrium potential and the activity of the reactants that are involved in the electrochemical reactions. So now coming to the derivation of the Nernst equation. So according to the first law of thermodynamics, we know that delta U is equal to Q plus W. So where we know delta U is the change in internal energy of a system, W is the work done and the system that is work done on the system, and here Q that we can say amount of heat that is absorbed. So here we know that the mechanical work here is given as minus P del V. So we can write W is equal to minus P del V plus the electrical, that is the sum of the mechanical work and the electrical work, that is minus P del V plus W electrical. So here also we know that entropy of a system is equal to Q by T, which shows that Q is equal to T del S. Then now substituting these values in equation 1.10, we can see delta U at constant temperature and pressure. This becomes T del S minus P del B plus W electrical work. Then also we know that the change in enthalpy is given as del H is equal to del U plus P del V. So at constant temperature gives free energy. Del G is given as del H minus T del S. So substituting all the values in the above equation, we find that del G at constant T and P, it becomes W electrical, that is the electrical work done. So now we will consider a galvanic cell which has two terminals. When Q charges move through the external circuit, then we can write W electrical as E into Q. From Faraday's law, we know that Q is equal to NF, and this F is equal to Faraday constant given as 96494 coulombs. So substituting here all the values, we can ultimately find out that delta G is equal to minus NFE. So here this is the gives free energy that is related to electrical work done. So now we will put this equation for the chemical reaction and derive the Nernst equation. So for this, we will consider a chemical reaction of this type that is represented in one equation 1.22. Then the delta G, that is the change in free energy, is given as delta G is equal to delta G0 plus RT ln concentration of the products divided by concentration of the reactants. So here this equation in 1.23, here we know R is the universal gas constant, temperature T is the temperature in Kelvin scale, delta G0 is the Gibbs free energy in their standard state. So here we can write delta G0 is equal to minus NFE0, where E0 represents the standard redox potential. So substituting all the values, here we find the equation that is shown in 1.25. Then we will divide this equation by minus NF. So ultimately we get that E is equal to E0 minus RT ln of concentration of react products by concentration of the reactants. So or converting this ln to log value, this equation can be obtained by from the value of 2.303. So here this is the most used form of the Nernst equation. Then now what we will do is we will substitute the standard values of R and F in this equation 1.28. So after substituting, it has been found that E is equal to E0 plus 0.0591 by N into log of the concentration of the reactants by concentration of the products. So here N represents the number of electrons that take part in the transformation process. So this is the standard form of Nernst equation that is widely used. So this is called as the Nernst equation. So here one example it has been given. So for this is a Hubsan reaction for a metal M that has been shown at 25 degrees centigrade. So for this reaction, the E can be written as E0 plus 0.059 by 1 by M plus log of Mn plus. The log of the concentration of individual metal is 1. That is why the denominator is written as 1 here. Now for a more general reaction of this type that is shown in equation 1.32, we can write the Nernst equation. Here it is shown. So now applying different types of, so for here the reaction of MnO4 minus forming Mn2 plus, the Nernst equation can be written in this way. So this is how the Nernst equation has been used for various types of reactions to determine their EMF. Now coming to cell potential. So the potential difference between the two electrodes, that is the hub cells, connected properly to form a galvanic cell when no current flows through them, it is called as the cell potential or EMF of the cell. It is also measured in volts. However, under certain conditions, when the current flows through the cell, the method of measurement of EMF values has been found to be lower than that of the actual values. So there are certain factors, but there is no method of measurement is possible for actual determination of the flow of current through the cell. So therefore, what happens is the cell potential is measured by a null point with a potentiometer, which involves balancing the cell output against an identical and standard. So the cell potential can be measured theoretically by using the nonce equation. So for this purpose, the calculation are there done in two ways. So in first way, the potentials of the individual electrode using the nonce equation for each electrode is calculated. Then the higher value of the reduction potential, that is more positive, that is more positive of the potential of the electrode, indicates that it will act as a cathode, and it is written on the right side, whereas the less positive value, it indicates the anode, and it will be written on the left side. That is, here E cell is equal to E right minus E left. In other ways, we can also calculate the E cell by first calculating the E0 and then finally by this equation. So here an example has been shown how we can calculate the E cell of a reaction. For this particular reaction, the activity of zinc and the activity of copper has been indicated. Their standard potentials have been also given. Then directly using the nonce equation, here substituting the values, we can find out the total EMF of the cell, and this is an alternative method of calculation. So this equation directly gives the value of calculation of the EMF of the cell. Then coming to classification and overview of electroanalytical methods. So a variety of electroanalytical methods are there. So first we will study a general classification of these electroanalytical methods. So the classification is based on the particular electrical property or the properties measured by keeping the other quantities constant. And the second is the mode of mass transport as diffusion, convection, and migration. So further, there are techniques that have been divided on the basis of procedures that have been adopted for analytical determination, such as the methods in which there is little or no chemical transformation occurs, and the measurement of an electrical quantity, it gives a direct measure of concentration, or that is indicated by direct, such as direct potentiometry. So this is the one method, and the second method, it involves the methods that are based on titration procedures. Okay, and this is, they are called as titration, such as potentiometric titration, amperometric titration, etc. So now we will discuss about potentiometry. So potentiometry means the measurement of potential at zero current flow. So it is also known as direct potentiometry. When it is direct, we utilize the single measurement of potential, and the nonce equation is used to calculate the cell potential. So the LJP and activity coefficients, they influence the value of the cell. So in the other way, that is the titration, potentiometric titration, what happens is a set of measured potential is used to detect the changes in concentration that occur at the equivalence point. So in this titration, the changes in the potential is important. So first we will talk about direct potentiometry. Since this technique is direct, we measure the potential difference between two electrodes immersed in a solution and connecting the cell, so that so formed a large voltage measuring device. So the cell formed by the two half cells and the solution is known as the galvanic cell. So the net cell reaction can be considered as the sum of two half cell reactions, in which the each half cell reaction is represented of, it represents the actual chemical process. Usually one of the half cell reaction that is chosen, it is termed as the reference electrode. The potential of the other electrode is a function of the concentration and it is called as the indicator electrode. So under these conditions, the cell EMF is given as E indicator minus E reference plus that of the EJ, that is the liquid junction potential. So this is how we can calculate. Now the concentration of the solution is determined by the single measurement of cell potential applying the non-stick equation, and from the calibration curve of E cell versus logarithm of the concentration, we can know the concentration of the reacting species. So here it is important that the indicator electrode, it should selectively respond to the species of analytical significance. A common type of indicator electrode for potentiometric measurements, it consists of a metal in contact with a solution. So such an electrode, it responds to the redox potential, and a inert metal such as platinum, it is immersed in a solution containing Fe3 plus and Fe2 plus, can also be used as a indicator electrode. So several electrodes with good selectivity, they are based for such development of potential across a membrane, and they are generally called as ion selective electrodes. So then the glass electrode has been commonly used for pH measurement. It is also an ion selective membrane electrode. The selectivity and the wide range of the conventional glass electrode makes easy for the determination of the pH, and it has been used in analytical application. So here that instrument is called as a pH meter, and it measures the pH. So and sometimes it can be either digital, or it can be set manually. Then coming to potentiometric titrations. So the most common application of potentiometry is the potentiometric titrations. So here in these titrations, the potential between appropriate indicator and the reference electrode, it is monitored during the titration process. So the titrations, they can be performed manually or with an automatic titration equipment. So let us consider this redox titration given in equation 1.43. So now if the above in this reaction, the potential of the titration is carried out, so the indicator electrode here, it should be such that it responds to a component of the above reaction. So the amount of reactant that has calculated, it is measured once the equivalence point is reached. Then how can we know the equivalent point? So it is determined by the following procedures, like tangential method, first derivative method, or the second derivative method. So using by any of these three methods, the equivalence points can be known from the potentiometric titration curves. So that is how one important use of potentiometric titration. Now we'll talk about voltammetry. So voltammetry, here what happens is, then electroactive species is either oxidized or reduced at the surface of the indicator electrode in a electrolytic cell. So the resulting current due to the electron transfer, it is measured as a function of applied potential. So such electrolysis, it is carried out under controlled conditions of diffusion. In diffusion layers, the electrolysis measures only a thin layer of solution that is adjacent to the electrode that undergoes electrolysis. So here in such processes, the electrical variable, it is directly proportional to the concentration of the bulk, and usually the time of electrolysis is very short. In voltammetry, we study the relationship between the current and electrode potential and their applications in chemical analysis. On the polarization of the indicator electrode, where the other electrode, that is the reference electrode, remains unpolarized, and it does not influence the shape of the IE curve. So this will be discussed in later sections. So now coming to polarography. So here polarography is it is various types of electrodes. They have been used in voltammetry, but one of them is very important and we call them dropping mercury electrode, DME, and it is very useful for measuring the corresponding voltammetric method, and this process is called as polarography. So the dropping mercury electrode, that is DME, is composed of a capillary connected to a mercury reservoir. The bore of the capillary, the length of the capillary, and the head of the mercury, they are adjusted in such a way that a drop is uh, comes out every 2 to 5 seconds. So a platinum wire, it is immersed in the mercury reservoir, and the DME, it is coupled with a unpolarized electrode. So polarography consists of electrolyzing a solution of an electroactive substance, that is between a DME and some reference electrode. The DME is the cathode and the reference electrode, it acts the anode. So the area of the anode is large correspondingly, so that it may be regarded as the unpolarized, and the potential of such electrode, it remains constant. So the current potential characteristic, or the IE curve, it can be studied with an apparatus. Here it is shown in figure 1.5. This is a manual polarographic circuit where the voltage is supplied to this cell, and it is adjusted by the potentiometer P. Here it is given the current through the cell. Here it is made by the reading on the galvanometer G. So this is, here is the G, and the current can be known from the value of G. So, on applying the potential between two electrodes and increasing its value in a stepwise manner, the following processes take place. At first, only a small current it flow through the so-called residual current. This continues and this reaction it occurs. So afterwards, a steep rise in the current is observed, and it will continue to rise with increasing potential till it reaches a maximum value. Here is the IE curve for the polarigram. Here we see first there is a slight increase, then there is a steep increase, and finally there is a saturation from this IE curve, that is the polarigram. So the conditions are set such that the diffusion is the main process of mass transfer. The limiting current under these conditions is known as diffusion current, which is called as ID. So the factors that affect the diffusion current was has been given from the Ilkovic equation, that is given as ID is equal to 708 nm to the power 2 by 3 into capital T half T 1 by 6 into C. So here small n, it represents the, in equation 1.1444, the small n, it represents the number of electrons that is consumed during the reduction process. Capital D is the diffusion constant, small m is the rate of flow of mercury, T is the time of flow, and C is the concentration of the metal ion that we have taken for the reaction. And the term 708 is the combination of different constants and factors that have been taken in designing this equation. So alternatively, we can write this equation as ID. From here we know ID is directly proportional to C, or we can say that ID is equal to Kc. So this K is a constant, and it is evaluated from the value of the current. So the curve here that is shown in figure 1.6, it is called as IE, or polarogram, or polarographic curve. Now from two important features of a polarogram are the half-wave potential, that is E half, and the diffusion current. Now we will further study this in the polarography chapter. Then coming to amperometry. So here in polarography, we see that the limiting current, it depends on the substance concentration of the substance only. However, if we reduce the concentration of the electroactive substance, then by interaction with another substance, then the current will be reduced. So this principle here, it is made to get the equivalence point, and this principle gave rise to the amperometric titration. So amperometry titration is based on the measurement of the current that flows through the cell at a suitable voltage, constant voltage, and it is measured as a function of volume of the titrant or as a time. So amperometric titrations, they are much more accurate than voltammetric methods. These titrations, they can be performed even when the substance is not very in there, that is they are very less reactive. So on plotting the data for current versus volume, we get straight lines having different slopes. So to calculate the equivalence point, so here uh, extrapolation of the linear segments may be done, and that is the microelectrode, that is the indicator electrode, may be a DME, a solid state platinum electrode, or a rotating platinum electrode. So or also an electrode of any other inert metal. Then now coming to electrogravimetry and coulometry. So here two analytical techniques, they are based on the quantity of the current and the amount of substance that has been consumed during the oxidation or reduction process. So these two methods are electrogravimetry and coulometry. So electrogravimetry is the oldest electroanalytical technique, and it involves the controlled potential reduction of a solution. It is used as a means of chemical transformation, and after the chemical transformation, the weight of the substance is measured before and after the transformation. That is why it is called as electrogravimetry. So this method is very simple, and it has been used for the analysis of a single element. So the metallic, after the process deposition occurs, the metallic deposits, they should be smooth and dry, and then they, after drying, their weights are taken. So and then we can know the types of the reaction that has been undergone. Then coming to coulometry, so when the amount of the constituents is not weighed but calculated from measuring the quantity of electricity by using the Faraday's law, then we call it as coulometry. So in these methods, the analyte is converted to different oxidation state by passing through the electrolytic cell. Now in primary coulometric analysis, the substance being determined, it may undergo reaction at one of the electrodes. In secondary coulometric analysis, the substance may react with another substance that is generated during the electrode reaction. So here in coulometric analysis, which proceeds with 100% current efficiency, so we get the quantity of species can be calculated by using the Faraday's law. Now we know that as per Faraday's law, the amount of chemical change caused by electrolysis is directly proportional to the amount of electricity that is passed through the cell. So for this reaction, O plus Ne forming R. So equating the Faraday's law, we can write the number of moles of the analyte is equal to Q by NF. So N, small n, represents the number of moles, F is the Faraday constant, and Q is the quantity of electricity that has been used. So the value of Q we can determine for a constant current, and it can also be determined for a variable current. Now, coulometry has been classified into two types: potentiostatic coulometry and amperostatic coulometry. So, potentiostatic coulometry means the coulometry at constant potential. So, the potential of the working electrode is maintained at constant level. So, only the analyte it gets oxidized. Here the current is initially high, but it decreases gradually with time. And graphically, here it has been shown in figure 1.7 for potentiostatic coulometry. Then coming to amperostatic coulometry, it means the coulometry is performed at constant current. So here it is, and it can be measured by an amperostat. So here Q is proportional to the quantity of the electrolyte, and here in these titrations, the titrant is generated at one of the electrodes. So these reaction may take place on the same electrode or on other electrode. The reagent can be generated externally, which removes the interferences, and such cell has been used to generate H plus and OH plus ions. Then coming to conductometry. So conductometry are the methods that involve the charge transfer by the ions in solution, that is the migration of the ions in solution. So here the principle of the Wheatstone bridge, it can be used to measure the conductance of these solutions, but certain points need to be kept in mind. That is, since a direct current polarizes the electrode in the conductivity cell, then to avoid polarization, alternating current must be used. The second point is a suitable conductivity cell with two different plating electrodes is placed in one end of the bridge. Since the cell also acts like a small capacitor, therefore to balance its capacitive reactance, a variable capacitor must be inserted into the bridge. So in conventional conductometric methods, an AC frequency of 50 to 100 cycles per second is used. So in these methods, the electrodes are not in immediate contact of the solution, but they are separated from the walls by using some dielectric material. Then coming to classification and relationship of different analytical methods. So here in figure 1.8, we can see the classification of different electroanalytical methods. So electroanalytical methods have been broadly classified into two types: interfacial methods and the Bolt methods. The interfacial methods are further subcategorized as static and dynamic methods. The static methods, they include potentiometry and potentiometric titration. The dynamic methods, they include controlled potential and constant current. The controlled potential, it further subcategorized as constant electrode potential coulometry, voltammetry, amperometric titrations, and electrogravimetry. The analytical methods, electroanalytical methods, which occur at constant current, they are further subcategorized into coulometric titrations and electrogravimetry. Now, the bulk methods in electroanalytical methods, they comprise of two processes. One is conductometry and the other is conductometric titrations. So these are some of the processes in different analytical, electroanalytical chemistry and their relationships. These processes will be discussed in later part. So with this, unit 1 is over. Now we'll just take a short break of 5 minutes and then again resume with unit 2. So now we'll start with potentiometry. Um, so before discussing potentiometry, we'll have a brief introduction about the nonst equation that we studied in the last unit. So here, nonst equation for in zinc sulfate solution can be given by this equation, and the potential difference can be written as E is equal to E0 minus RT by NF ln of 1 by activity of the metal ion concentration. So here this is the nonst equation that we had talked of. Now in this equation, no term for the metal, that is the elemental metal, it is here in the logarithmic term, because we know that the activity of the metal in its solid state is always equal to 1. So here in this equation 2.2 can be converted to its log form by multiplying 2.303, and here it is given in equation 2.3. However, for most purposes, we can write am plus by in the form of concentration of, that is the activity of the Mn plus metal ion can be written as the concentration of Mn plus, and here in equation this is the final, the simplest form of nonst equation that has been widely used, that is represented in equation 2.4. Now here some of the questions have been given regarding the calculation of nonst equation. Then coming to measurement of potential. So the electromotive force developed by a galvanic cell, it cannot be measured accurately. So here in figure 2.1, we see this is the circuit diagram for a laboratory potentiometer. So here potentiometer is one of the types of instrument, simplest types of instrument that measures the potential. So here potential meter with a potentiometer, we call it, this is the laboratory potentiometer. So this potentiometer has been divided into two parts, that is the voltage divider and the galvanic cell. So the working battery that is been used here with the resistance formed from the point A to C is directly proportional to the length of the AC. That is, RAC is directly proportional to the length of AC, or KAC, where it is K is the proportionality constant. So then a sliding contact, it permits the variation of the distance A and C, and thus the output voltage. So the divider is precision wire wound resistor. It is formed in a helical coil. So the potential of the working battery EB is greater than that of the standard cell potential EX or ES. So the principle of this potentiometer is that a current I, it flows continuously from the battery through AB, causing a potential drop between A and B. So from Ohm's law, we can write EAB is equal to EI into resistance of RAB. So the current passing between A and C is also given as EAC is equal to IRAC. Now we know that the resistance along the resistor is linear in nature. So we can write the following above equations in terms of E is equal to IRAB is equal to K into I of AB or K into I of AC. Now dividing the above equations, two equations, we see that EAC is equal to E into AC by AB. So now there are three possibilities. Exit if the potential divider is adjusted to position ESC and the key case is placed. So here equation 2.9 with the standard cell and the unknown cell, but we can write it as E of S and E of X to be, that is shown in equation 2.10 and 2.11. Then dividing all these equations and rearranging, we can find the cell of an unknown potential, that is EX is equal to ES into AC into AC. So here it is given in equation 2.12. Now coming to standard cell. So we have seen that there is a need of standard source for measurement of potential. So the most commonly used standard cell in potentiometry is the Western cell, or we call it as the Western cadmium cell. So here, which is also given in figure 2.2. Here it is shown the in figure 2.2, the western cadmium cell. So it has been represented by equation 2.13, that is cadmium, mercury, CdSO4, 8 by 3 water solid in Hg2SO4 and mercury. So the cadmium mercury represents the solution of cadmium in mercury. The two half cell reactions occurring in this cell are given in the equation 2.14 and 2.15. 15, the two half cell for the western cell has been written, and the total cell reaction can be given as Cd plus mercurous sulfate at 8 by 3 H2O, and here it is the final form. The potential of this western cell is 1.0183 volt at 20 degrees centigrade. It is temperature dependent and it is given by 1.0183 minus this factor at any other temperature. However, this is, since this is temperature dependent, we can find the use of this equation. So a typical design for the western cadmium cell, here it has been shown in figure 2.2. So here we can see one side is cadmium and mercury, that is the CD amalgam here, and here it is HgSO4 and it is Hg. The potentiometric measurement using potentiometer, it is suitable if the galvanic cell having internal resistance less than 10 to the power 3 ohm. Most of the cells containing membrane electrode like the glass electrode, they have very high internal resistance of greater than 10 to the power 9 ohm. To measure potential of such high resistance cell accurately, it is necessary that the voltmeter device have resistance that is several order greater than that of the cell being measured. Now, if the meter resistance is very low, then the current is drawn and there is a negative loading error. So because of this, digital voltmeters, they are preferred for the measurement of potential because they have large potential resistance of 10 to the power 11 to 10 to the power 12 ohm. These digital voltmeters, they are called as pH meters or ion meters. Then coming to direct potentiometry. Potentiometric methods of analysis, they may be grouped into direct reading method or direct potentiometry and potentiometric titrations. So in this section, we will talk about the direct potentiometry in details. The direct potentiometry method is the method which makes use of the single measured electrode potential to determine the activity of the ion of our interest. Now, this method is widely used for the determination of the pH, that is the hydrogen electrode, or determinations of other ions using the ion selective membrane electrode. So, in all other electroanalytical methods, two electrodes are required. However, one is the potential, one is the standard electrode, the other is the reference electrode. The second electrode, whose potential is dependent on the concentration of the ion to be determined, is called as the indicator electrode. So for direct potentiometric measurement, the potential of the cell can be expressed in terms of the indicator and reference electrode, and here it is given by equation 2.16. The Ej represents the potential of the liquid junction, that is the junction potential. Now let us consider an electrode whose potential vary with cation activities or concentration, and then we can write the equation similar to that of Nernst equation in terms of equation 2.17. Now substituting the values of 2.17 in equation 2.16, we get equation 2.18, and ultimately finally we get the value of in terms of Pm here, that is minus log of Am plus n of cell minus k by this equation. On reversing, we have P of A, that is Pm is the negative logarithm of the metal ion activity and Pa is the negative logarithm of the anion, and that is how they are represented. Here the k in the equation 2.21, it represents the summation of all constants. Now, all direct potentiometric equations, they have been based on these equations 2.20 and 2.21. So here they can be simplified in terms of E cell is equal to K minus 0.059 by 1 by N into P of M, and here in equation 2.23. So now using these equations, we can determine the concentration of metal ions or cations and anions in terms of Pn and Pa. Further, the equation also indicates that for a metal ion selective electrode, an increase in the metal pH, the negative logarithm of the metal ion, it also results in decrease of the E cell. In the electrode calibration method, K is determined by measuring the E cell for one or more standard electrode of known PM or PA. This calibration is performed just before the determination of PM or PA for the unknown. Now we assume that K is unchanged when standard is replaced by the unknown analyte solution. Sometime instead of calculating K using EMF value of standard solution, a calibration graph is plotted using measured EMF of standard solutions against the log of the concentration. So then by further plotting the graph, we can use the graph paper, and from the logarithmic values, that is called as the semi-log paper, we can directly get the concentration of the sample. So this is how the pH is, the potentiometer. Here it can be, this equation can be used. Then coming to reference electrodes. So we know that one of the half cells of the galvanic cell, it is consisted of the solution under investigation and the indicator electrode. So this potential is varied in accordance with the Nernst equation. So we also have the reference electrode that is also used in potentiometry. So now we should understand some of the certain features while selecting a reference electrode. Like the potential of the electrode, it should remain constant even if some current is passed through it. The potential should be reproducible. The electrode should be easily prepared from readily available materials. The potential of the electrode should not change with temperature, and it should be cheap. Now coming to hydrogen electrode. So we all know that the standard electrode potentials are quoted in reference to the standard hydrogen electrode or SHE, so which is the most important primary reference electrode. So upon connecting the standard hydrogen electrode with a metal electrode through a bridge, the standard electrode may be obtained from the following. Here in equation figure 2.4, we see the common design of a hydrogen electrode. Here in figure 2.4. Now, the hydrogen ions of the solution and the gaseous hydrogen, they are kept in equilibrium, and platinum electrode coated with a thin film of platinum black. The platinum electrode is cleaned with chromic acid and it is thoroughly washed with distilled water. Then it is electrolytically plated from a solution of chloroplatinic acid with platinum foil taken as the anode. It is very important here to note that a thin jet blackhead deposit is formed, and the thick deposits are not satisfactory for hydrogen electrodes. That is why after platinizing, the electrode has to be made free from chlorine. So the most convenient source for hydrogen is the compressed gas that is available in the market in the form of hydrogen cylinders. So the gas is purified by passing through glass bottles containing zero point 0.2 molar potassium permanganate and alkaline pyrogalol dilute H2SO4. So here we see figure 2.4 shows the diagram of a hydrogen electrode. So even though the hydrogen electrode, it's the primary reference electrode, other standard electrodes have also been developed in for day-to-day applications. So hydrogen electrode is inconvenient in certain laboratory experiments because it has some very important problems, like hydrogen requires a large gas cylinder, the hydrogen air mixture is highly explosive in nature, and the catalyst is easily poisoned. So this is how the why certain points that needs to be considered while we select a hydrogen electrode. Hence, for routine laboratory processes, what we do is the other reference electrodes, they are commonly used. The potentials of the reference electrodes, they are measured against standard hydrogen electrode, and in potentiometry the potential is expressed if it is taken in reference to the SHE. So the simple and common reference electrode that are widely used are the calomel electrode and the silver chloride electrode. So these two electrodes, they are preferred because they are very easy to prepare and they maintain a constant potential. So their potential does not vary with time and they are highly easily prepared. So that is why we come across calomel electrode. So this calomel electrode is the most widely used electrode because of its preparation method and its potential remains constant over a period of time. Now, a calomel hub cell is one in which mercury and calomel, that is mercury 1 chloride, they are covered with aqueous KCl and that is mostly zero point 0.1 molar saturated. If the KCl solution is saturated with calomel, then the electrode is called as saturated calomel electrode. The electrode potential of such saturated calomel electrode is plus 0.24 volt at 25 degrees centigrade, and that has been determined with respect to the standard hydrogen electrode. Now if the KCl solution is exactly 1 molar, then the potential is 0.28 volt, and this is sometimes called as the standard calomel electrode, that is SCE. So here in table 2.1 we can see the certain concentrations of specifications of calomel electrodes. Now the Hubsel electrode reaction for such calomel electrode is given here in this equation 2.24. So now we know that mercury is a dimeric species and that here we are dealing with Hg plus ion. So hence, according to the non-stick equation, the potential can be given by equation 2.25. Now we know this Ag2 2 plus is involved in another equilibrium. So we can find write the solubility product in terms of Ksp is equal to Ag2 2 plus into concentration of Cl minus. Then substituting the above values, we find E is equal to E0 minus 0.0591 by 2 concentration of chloride ion by the solubility product. So here we see that since E0 and the Ksp are constant, we see that the E reflects the concentration of the chloride ion that has been taken uh, in the KCl solution. So the calomel electrodes may be fabricated in a variety of shapes and sizes. That some of these has been exemplified here in figure 2.5. Here in figure A, it is a laboratory made saturated calomel electrode, and here it is A and B, and the C is a commercially available calomel electrode. So calomel electrodes, they are small enough to be inserted into the vessels of animal experiments through the syringe needles. So here it should be emphasized that the potential of an electrode does not depend on its size. So because the liquid junction potential, the molarity or the concentration of them has to be maintained. So although the contamination from calomel electrodes is not important, however, it should be remembered that there are possibility a few amount of KCl might leak into the solution. So hence precautions must be taken accordingly. Now, for special purposes, modification of the calomel electrodes has been done. So, thus, if it is necessary to avoid K plus ions, the electrode may be prepared using NaCl instead of KCl. So, it has also been found that the presence of chloride ions and mercury may be used, and hence they can also be used mercury sulfate or potassium or sodium sulfate. Now, silver chloride electrodes are another reference electrodes that have been widely used, and here it consists of a silver plated platinum wire and it is immersed in a solution of potassium chloride. So it can be written as AgCl saturated KCl Ag, and the half cell is given by equation 2.30. So here the when this electrode is prepared with saturated KCl, then at 25 degrees centigrade its value is 0. Plus 0.199 volt at 1 molar of KCl, and zero point 0.1 molar of KCl it gives this much value. So this is with respect to SHE. So this electrode, it can be constructed very easily, and here it has been shown in figure 2.6. The electrode, it is placed in a glass tube and it is fitted with a 10 mm glass disc or a porous plug here as it has been shown. So KCl or agar gel, it has been placed at the solution to prevent the loss at the to prevent the loss of the solution. Then the tube, it is filled with saturated KCl. Then a drop of 1 or 2.1 molar silver nitrate is added, and a heavy Ag wire is inserted into the solution. So this is how a silver chloride electrode is constructed. Then coming to indicator electrodes. So an indicator electrode of a cell is one whose potential, it is dependent on the activity of a particular species whose concentration is to be determined. Now several metals like silver, copper, mercury, lead, cadmium, they are used for the construction of such type of indicator electrodes. So their potentials are reversible and they reflect the activity of the ions in solution. So among the metals, some metals like nickel, cobalt, tungsten, they do not give reproducible potentials due to some chemical or physical reactions, and hence they are not as used as indicator electrodes. So usually these metal electrodes, they are constructed from coils of wire flat metal. Here it is shown in figure 2.7. We can see how different designs of indicator electrode they have been used. So large surface area is preferable. Then metal surface is to be thoroughly cleaned. Usually it is achieved by dipping in concentrated nitric acid followed by rinsing with distilled water. In addition to the above, where the metal electrode is used as an indicator electrode, it can also be used indirectly where it becomes responsive to anions. For this application, it has to be saturated with another sparingly soluble silver salt. So the reactions that are involved in this equation has been given by 2.31 and 2.32. So when we combine the above equations and apply Nernst equation, we finally get the EMF to be this. So this type of electrode where silver serves as the indicator electrode for iodide is called as an electrode of the second order because it measures the concentration not directly but indirectly from an by comparing with another species. So if it is used for determination of silver ion, then it is the electrode of the first order. Then coming to mercury electrodes. Another important second order electrode used for the measurement of EDTA and its anion Y4 minus. It is based on the response of mercury electrode in the presence of a small concentration of stable Hg2 EDTA complex. The Hubsen reactions for this electrode process are similar to the one that is given, and here it can be written in equation 2.35. So for which we can write the Nernst equation of this type. So for this electrode, a small concentration of HgY2 minus, it is introduced first into the analyte solution. The complex is so stable that the dissociation to form Hg2 plus is minimal. Here we can see 6.3 into 10 to the power 21, and the concentration of the complex remains constant over a wide range of Y4 minus. Hence the above equation may be simplified as E is equal to K minus 0.0591 by 2 log of concentration of Y4 minus. And then where the constant K is equal to this value. Then this electrode, mercury electrode, has been largely used in complexometric titrations involving DTA. Then coming to membrane or ion selective electrode. There is another category of electrodes called membrane or ion selective electrodes. These electrodes, they preferentially respond to a single type of chemical species. The potential between the indicator electrode and the reference electrode varies as the concentration or activity of that particular species, it varies. So unlike the inert electrodes, ion selective electrodes, they do not respond to all species in solution. Glass membrane electrode or glass electrode is a typical example of ion selective electrodes. So functioning and of the glass electrode, it is discussed in the next unit. Then coming to determination of equilibrium constant. So from electrode potential measurements, we can calculate numerical values of many equilibrium constants such as solubility product constant, dissociation constants, and formation constant. One important advantage is that the measurements can be made without disturbing the equilibrium between the solution. So now we know we have that delta G, that is the change in free energy. It is given as delta G0 plus 2.303 RT into log of K, where K represents the equilibrium constant. Now we know that during equilibrium, delta G is equal to 0. So this implies that delta G0 is equal to minus 2.303 RT log of K. Also, we know that delta G0 is equal to minus NFE. So, combining these two equations, we find that minus NFE is equal to minus 2.303 RT log of K. So, we get log of K is equal to this, and substituting the values of F, R, and T, we find the ultimate equation, that is log K is equal to N into E0 of cell by 0.0591. So this is how the equilibrium constant can be calculated from the cell value, cell EMF. So here one equation it has been given, and how we can find out the solubility product from this data. Then coming to potentiometric titrations. The potential of suitable indicator electrode, it is used to establish the equivalence point during a titration. So we know the purpose of a titration is find out the endpoint or the equivalence point. So in such type of potentiometric titrations, determination of equivalent points is done by the potentiometric titration. So it provides different information from a direct potentiometric measurement rather than involving absolute potentials. The equivalence point it will be revealed by a sudden change in the plot of EMF versus the volume of the that we have plotted from the graph of the EMF versus the volume of the titrating solution. So one electrode it must be maintained at constant but not necessarily known. The other electrode must serve as the indicator electrode. So in contrast to direct potentiometric measurements, the potentiometric titrations generally they offer accuracy. So here the accuracy is increased because the measured potentials they are used to detect rapid changes in activity that occurs at equivalence point of the titration. Furthermore, if there is a change in EMF versus the volume, then rather than the value of the EMF, then the liquid junction potential activity has to be minimized. Potentiometric titrations may be applied to a variety of systems, including those involve oxidation reduction, precipitation, acid base, and complexation equilibria reactions. Now, these have been discussed in this section. The potentiometric endpoint detection also provides accurate results than the normal conventional titration methods. So it is particularly useful for titration of colored or opaque solutions and for detecting the presence of unsuspected species in the solution. Titrations of more dilute solutions are possible using potentiometry. However, unfortunately, such titrations they are very time consuming and while performing with an indicator. Now here in figure 2.8, a typical apparatus for potentiometric titration has been shown. This is how a lab setup for a potentiometric titration. So here the titration involves measuring and recording the cell potential after the addition of the titer from the burette. The titrant is added in large increments at the outset as the endpoint is approaches. So the increments are made smaller. So sufficient time must be allowed for the attainment of equilibrium after each addition of the reagent. The precipitation reactions they require several minutes for equilibration and particularly in the vicinity of the equivalence point. So here when we are reaching near the equivalence point, the the titration or the values must be lowered so as to know the exact value of the equivalence point. So a number of commercial potentiometric titration units are available which comprise an electrode system, and that is together with a special stand providing the supporting for the electrodes here. Then the location of the endpoints. In the potentiometric titration, the endpoint is detected by determining the volume at which a selectively large change in potential it occurs as the titration is added. The method can be applied for the reactions for different types of titrations like acid basis, reduction, precipitation, and complex titrations. In manual titrations, the potential is measured after the addition of each successive increment of the titrant that is added from the burette, and the readings they are plotted on the graph paper versus the volume of the titrant. So here in figure 2.9a, here we can see this is the EMF that we measure versus this is the volume of the titrant that has been kept on adding, that is in figure 2.9a. So this we see the increase is not linear and it acquires a sigmoidal shape. So the change in EMF is greater around the equivalence point. In fact, the equivalence point here, to know the actual equivalence point, here in figure 2.9b, here we see in the x-axis it is d of E versus the change in volume dV that has been delta V. It has been plotted in figure 2.9b, that is here it is shown. So the resulting curve it rises to a maximum equivalent point. The volume at equivalence point is determined by dropping a vertical line. Here we will drop a vertical line from the maxima, and this vertical line it will give us the location of the equivalence point. Now here when we look into figure 2.9c, it shows the plot of the change in the slope of the titration curve, that is del square E by del V square against the, here in x-axis we have taken the volume of the titrant. So here then at the point where the slope of this del E square V by del V square is maximum, the derivative of the slope is 0. Here the equivalence point, and here the end point is located by drawing a vertical line. By here we draw a vertical line, then we calculate the end point. Then coming to the discrimination between the endpoints can be made easily. An approximate numerical value for dissociation constant of the reactant species can also be estimated from potentiometric titration curves in theory. This quantity can be obtained from any point along the curve as a practical matter. It is most easily calculated from the pH at the point of half neutralization in the titration of weak acid HA. So here we can write the dissociation constant Ka for the weak acid HA is H plus A minus by HA. Then taking log values of both the sides, we find that pKa is equal to pH minus log of concentration of A minus by log of concentration of acid. Now at half neutralization point during, so concentration of A minus is equal to concentration of HA. Therefore, we can write pKa is equal to pH, but this is during the half of the equivalence point. The equivalence point has totally not reached as this point. So here pKa is equal to pH. Therefore, the pKa values can also be directly read from the, can be known from the titration curves. It is important here to note that a dissociation constant determined from a potentiometric titration curve may differ from that shown in the table because the latter is based upon the activities. So, oxidation reduction reactions. The indicator electrodes for oxidation reduction, they are generally fabricated from platinum, gold, mercury or silver. The metal chosen must be unreactive with respect to the components of the reaction. It is merely a site for electron transfer. Platinum electrode has been most widely used for oxidation reduction reactions. It should always be recalled that the curves for many oxidation titrations, they are not symmetric. Thus, the equivalence potential may be different from the potential corresponding to the point. in the curve. So the determining factor in the values of potential is the ratio of the activity or the concentration of the oxidized and reduced forms of certain ion species. Like for this common reaction, the potential acquired can be given in equation 2.46, that is at 25 degrees centigrade. Then the potential of the immersed electrode, it is controlled by the ratio of these activities or concentration. So in redox reactions, the reducing agent is oxidized or oxidizing agent is reduced, and the ratio and the potential changes. So therefore, the titrations that involve like Fe2 and potassium permanganate or potassium dichromate may be followed, and by this process and the equivalence points can be obtained. Then coming to precipitation titrations. So here the titrations that involve precipitation reactions are not numerically they are so numerous. So one of the reasons they are very limited in nature. So one of the reasons that they are very limited is the lack of suitable indicators. So in some cases, particularly in the titration of dilute solution, the rate of reaction is very slow. As the equivalence point here, it approaches a higher degree of supersaturation, it does not exist, and thus precipitation becomes very low. So here the indicator electrode for a precipitation titration is frequently the metal from which the reactant cation has been derived. So theoretical curves for the potentiometric titration, they are readily derived. For example, we may describe the potential of a silver electrode during the titration. Here is given by the equation 2.47. So where minus 0.15 is the standard potential for the Hubsel reaction, and AgI has been for this Hubsel reaction. So the potential for this reaction can be given as E of Ag is equal to 0.799 minus 0.0591 log of 1 by Ag plus. Here 0.799 is the standard potential for the reduction of silver ion. Then coming to complex formation titrations. So both metal and metal electrode and the membrane electrodes, they can be used to detect endpoint in reactions that involve formation of a soluble complex. The mercury electrode, here it has been shown in figure 2.10, is particularly useful for EDTA titrations. It will function as an indicator electrode for the titration of cations forming complexes that are less stable than HgY2 minus here, and in figure 2.10 that has been a mercury electrode, it has been shown. Then coming to differential titrations. This titration requires the use of two indicator electrodes, one of which is well shielded from the bulk of the solution. Here in figure 2.11, we can see the differential potentiometric titration, and this is the setup for the differential potentiometric titration. So here in figure 2.11, it shows the typical arrangement. Here one of the electrodes, it is contained in a small side arm test tube. Then the contact with the bulk solution is made through a small hole in the bottom of the tube. Because of this very limited access, the composition of the solution surrounding the shielded electrode will not be immediately affected by the addition of the titrant to the bulk of the solution. So the resulting difference in the solution, it gives rise to a difference in the potential, that is delta E between the electrodes. So after each potential measurement, the solution is homogenized by squeezing the rubber ball that is present here, as you can see, several times. So as a result of squeezing this rubber bulb, delta E again becomes zero. So if the volume of the solution in that tube that shields the electrode is small, then the error will also be very small. So the main advantage of such a differential method is the elimination of the need for the reference electrode and a salt bridge. That is one of the most advantageous prospects of using differential potentiometric titration apparatus. Then coming to automatic titrations. Nowadays, we have a large number of automatic titrators that are based on the principle of potentiometry. These are highly useful in those places where a large number of routine analysis are done. These may not be more accurate than the manual techniques, but they are very rapid and decrease the experimental time. So, two different automatic titrators are: the first type gives titration curves of V versus E, or delta E versus delta, or delta E by delta V versus the volume of the titrant that is added. The endpoint is obtained from the curve by inspection. In the second type of titrators, the titration it is stopped automatically when the potential of the electrode systems it reaches a predetermined value, and the volume of the reagent delivered it is read at the operator's convenience. So these titrators usually employ a burette system with a solenoid operated value to control the flow, or alternatively it makes use of a syringe, the plunger, which is activated by a motor driven micrometer screw. So this is how a automated titration potentiometer or titrations works by potentiometric titration. So here in summary, today we have discussed about electrode potentials, the principles of potentiometer and the measurement of potential. We have also talked of different types of reference electrodes such as hydrogen electrode, calomel electrode, silver chloride electrode, and other different types of indicator electrodes. So then different types of titrations has been discussed, and these are some of the numericals and questions that you can go through. So with this, we finished the first unit that for today, that was about introduction to electroanalytical chemistry, and we have also finished the second unit today, that is about potentiometry part 1, so which concerns with different types of potentiometry. So in next class we will talk about the we'll talk about the greater details of potentiometry. So thank you for today.
Thank you, ma'am.